this computer. Now, so one thing I didn't explain yesterday about threads. So just wait till everyone is either connected. So you should have the connection by now, yeah. So I'm recording. Bring up my pen. And I bring up, of course, the highlight of it, me there in the corner. So when you've long gone from here and you're looking back in the video, you'll always see, Jesus, there's none. Okay? I'll always be watching you. Ooh, that's... Right. Now, so here is what I did yesterday now. I added 2 lines of code. All right? Now, so I created a list. And how did I do it? I used a, hold on, my thing is gone. Just give me a second. Panel, PC settings, setup. Okay. Nice. Now, so I generated 40 random numbers. Okay. Print them out. There's our 40 numbers. Okay. Right. Now, I print them out here, and when it's a single, when it's a stream, which is now the full term for this is actually a single threaded stream. Well, that's what I'd call it. It's a single threaded stream. Okay, that means each item that's produced by the stream is operated upon by one thread. So everything is done one after the other. All right. So you have only one thread operating on this list of 40 numbers. Okay. So what does it do? It prints off the first number, prints off the second number, prints off the third number, so on and so forth. Yeah. Okay. Now, okay, the internet is back again. It's really strange. So hopefully this doesn't stop the share. Now you didn't notice any hopping in the, is it still broadcasting to you there, is it? Is it? Okay, right. Now, so you have your 40 numbers, you have your single thread, I run it. You have your 40 numbers, you have your single thread. So you've run it now. So when you have a stream, that is a single threaded stream. Now, a parallel stream is something a lot different. Now, when a single threaded stream, that means only one item is going to be acted upon the list at the same time. Now, a parallel stream uses all your available threads. Okay, that's why you can't predict the outcome. All right. So what you have is, in my case, I have 16 available threads. So you have 16 threads operating on this string. So you have 16 numbers. You have 16 threads operating on 40 numbers. Okay? So it's 16 times faster. All right? Now, to prove that there is 16 threads in operation here and 1 thread in operation here, I put in this line of code here. So it runs, it produces 40 random numbers. Okay? And we can see the amount of threads is 1. Okay? Now, I do something similar with the parallel stream. Okay? And we can see the amount of threads down here is 16. Okay, so a parallel stream is significantly faster than a stream. Okay, now of course the main issue with a parallel stream is that you 16 threads that are going to be accessing 16 numbers at the same time. They're going to be accessing 16 different numbers, but they could be accessing any 16 numbers. All right, now let's
16 system threads.
yes, well it's 16 threads.
Yeah. But do they all, does each one count as a system thread? Does only one count as it?
There's only one. There's only one system thread, and there'll be 15 order threads. Okay, but it doesn't differentiate here. Okay, so now yours, I don't know, is there 4 or 8 threads in yours? There are 8, is it? Do you know what's in them?
4.
So just type in thread.activeCount, print it out, and tell me how many threads you have in your machine there. Now this will use all available threads.
It says 4 and 9, but I have some sort of virtual thing.
Yeah.
No, it's actually it's only hardware, 4 cores, low virtual power.
Okay, so it's, what have you got there? 4? Everyone 4 is it? Someone else check their machine there just to see.
Where do we get it?
Just type in thread.activeCount, print it out in Eclipse and see. Yeah, Jesus, that's okay. Just 4. So I've got 16. Okay, now yours is going to be 4. So now parallel streams are totally dependent on course, on how many cores you have on your on your machine. This is a quad core. It's got 4 cores per machine, so that's 16. 4, 4, 16. Okay. Now that means that any operation I'm doing here and here, this one is going to be 16 times faster. All right. In actual fact, it's usually more than that. All right. Now, the main problem with parallel streams is that you're going to have 16 actors accessing the stream at the same time. All right. Whereas here you only have 1. So yes, they are more difficult to manage. There's no doubt about that. But your performance, it's worth the bother. Okay. There is more bother using parallel streams than there is ordinary streams. All right. But it is worth the bother. Now, if you use a for each, the parallel stream, problem with that is that you actually do lose a lot of performance benefits. All right, because effectively what you're doing, this is a parallel stream that can have 16 things operating in it. And here, you're forcing it to go from the first item to the second item. So this basically turns it back to a single threaded. It acts like a single threaded application. So if you use a for each, it's effectively changing your parallel stream to a stream. You still have 16 threads that can use it, but it's operating as a single threaded. So what you can use instead is a for each ordered. Okay. Now this is, oh, sorry, I stand corrected. For each, sorry, I'll go back and do that again. For each, I need to rephrase that. I said that the wrong way around. All right. All of this is a parallel stream. Okay. When you use a for each with a parallel stream, that means you can have 16 threads accessing your stream at the same time. Okay. If you use for each ordered, that's going to change your parallel stream to basically a single threaded version of it. Okay. So you can see what we've done here, list that parallel stream. We're filtering it out to all numbers that are greater than 50. All right. And then for each ordered, that's going to put some order on it. All right. But for each ordered means only one thread can access your stream at a time. Now the filtering means that 60, because it's a parallel stream, means that 16 threads can access your stream at the one time. So it can be processing 16 numbers at the same time. Okay, so it's going to be, this part here is going to be 16 times faster, but this part here isn't going to be 16 times faster. Now, to make things even faster, there's another thing you can do here. All right, so if you use parallel streams like that, that part is going to be 16 times faster. You can even make it faster if you make that a thread safe list. Or no, actually that's correct. Okay, now list is not thread safe. Okay, list is not thread safe. So 16 threads can access that list at the one time. All right, it can, yeah. Okay, so that is a totally parallel operation, you could say. Okay, list.parallel stream, that's going to produce a parallel stream. Now, list is not a thread safe operation, not a thread safe collection, which means that you can have 16 threads operating on that list at the one time. Okay.
No, of those 40 numbers, they both trying to hit the same number together.
Well, no, because what you call it, the thread scheduler. You know, the thread scheduler. When you do a parallel stream, it operates something called a thread scheduler. They won't hit the same one at the same time. Okay. Now, in the older version of threads, you had to manage that yourself. All right. Now, in the older version of threads, you didn't have streams. All right. In the older version of threads, you didn't have streams. Now here, in the older version of threads, you could have a situation where you're trying to access the same stream at the same time. Now, if you use parallel stream, there's a thread scheduler, I think it's called, operating in the background, which ensures that two numbers aren't accessed at the same time. Okay. So list.parallel stream for each. That is a totally parallel operation. Okay. Now this down here, that's parallel, or that's multi-threaded. That part is multi-threaded. Now this part here, just take it all out, start it again. Okay, so that part is multi-threaded. And that part is multi-threaded. That part is not multi-threaded. Okay, now you still have your 16 threads, but it'll only allow one of those threads to operate in that at a time. So if you're going to use for each order, remember you're going to lose a lot of the benefits of the threads. Okay, so what are threads all about? Threads are all about improving the performance of your application. If you've got a small application and it's running fine as a single threaded application, well, then you don't need to use threads if you don't want to. But they do offer huge performance increases. All right. Now, you don't notice a performance increase for something like this. You got 40 numbers. All right. You're not going to notice any number there. Now, you only really notice the performance increase when you're using lots of variables or where you're doing really complex calculations. All right. Now, so this is 16 core. So it will be more than 16 times faster. It can be factors of thousands of times faster. There is an example down, we'll actually come to it today, might come to it before lunch, where without threads, it takes 40 seconds to do. With threads, it takes, I think it's something like 0.001 seconds. Okay, so that's a factor of, that's 400, that's 4,000, it's a factor of 40,000. Okay, that's a massive difference. Okay, morning, Andrew. No need to be sorry at all. Welcome. Okay, now, so we can see as soon as you engage a parallel stream, it uses all available threads. That's what a parallel stream does. Okay, so a parallel stream uses all available threads, which is 4 in your case, 16 in mine. Okay, now, so parallel stream, put it in here. Now I need to take same time by the maximum amount of threads on your system. In my case, it's 16 threads. So you have 16 threads accessing this stream at the same time. So in effect, it could be said to be 16 times faster. But in reality, it's often multiples of this. Thousands, in other words. All right, so this parallel stream, so this guy here, this is a multi-threaded stream. Okay, next one, list of parallel stream. So this is still a parallel stream. Here, for each ordered, so this part here, this only allows one thread at a time to access the stream at this point. But everything up to that is being multi-threaded. All right. So your stream can be a combination of multi-threaded and single-threaded. But parallel streams are all about making your application faster, more efficient. All right. And they do, now you can use streams as normal, but if you got some really, really complex calculation that's taking a long time to do, and you want to do this multiple times, well, then parallel streams is the way to go. All right. Now, obviously, there is issues with parallel streams. Now, the main issue is if you have let's just say 16 numbers. And we'll just say we have 4 threads. Now, I'm not sure how to do it, and it's not on the exam, but you can limit these parallel streams to a certain amount of threads. I'm not sure how to do it, but you can do it. It's not on the exam, all right? As far as I know, you can do that. You can limit the parallel streams to only to take 4 threads. Why you'd want to do that, I don't really know, all right? Because the thread scheduler is so efficient, if they're not available, they just won't use them, all right? So as far as I know, you can limit those to only a certain amount of threads. I'm not sure how to do it, but you can, I think. All right. So if you have 16 numbers, if you have 4 threads, let's say the numbers is 2, 3, 4, 5, 6, 7, 8, and 9. Just use those numbers. Okay. So you have 4 threads. So this thread is accessing this one, this one, this one, and this one. So that's T1. T2, T3, T4. Okay. Now, it probably won't access them in that order. All right. It may, but on the balance of probability, it won't. All right. Now, if you're just accessing values in a stream, then parallel streams are brilliant. If you're just taking a value inside here and calling a method on it, doing some calculation, then parallel streams are brilliant. Okay. Now, the problem arises is, let's say that I change these numbers again. And there's a relationship between the first number and the second number. Okay. They all go up by 2. 2, 4, 6, 8, 10. Fuck it. Fire now. Huh? Is that what? Yeah. Oh, yeah. Where's he gone? Someone's come back here. Someone's come back. Oh, yes, what's wrong with me? Are you following me out, folks? Stop it. Zoom recording. And it's nearly time to go to fucking. So. Now, so just to recap again, in that this guy here, okay, this is a parallel stream. So as soon as this kicks in, all of your threads, all your available threads are going to be operating on this stream. That's what parallel stream means. That's why you can't predict the order. All right. That's why they could print off that's when you use a for each, they could print off in any order. Why? Because in your case, you have 4 threads operating on this stream. In my case, you have 16 threads operating on the stream. And they're all operating at the same time. All right. So that guy there, that is a list which is that's not a thread state collection. So that means the 16 threads can be operating on the list at the same time. Parallel stream, that creates a stream where 16 threads can operate on the stream at the same time. For each, so the way the for each operates is that there is 16 threads going to be operating on 16 numbers. And what it's going to do, it's going to print off 16 numbers. Okay, and they're all happening at the same time. All right, so at the very minimum, it's going to be 16 times faster. All right, it can often be an awful lot more than that. Do you mind if I turn off the heat here? It's a bit hot. Okay, so I'll just turn it down. Right, now, so I'm just going to do a few more stream things down here. So that's static void ex1. And we can see here, this is 16 threads. This one here is only 1 thread. Now, that guy, thread.active count, what that means is how many threads are currently in operation. All right. Now, the reason it says 16 is, let me just see now, because that part is probably running in the middle of this. Do you understand that? So this part is probably running in the middle of this, because remember, parallel streams, that means you could have 16 streams operating at the same time. So at one stage, there could be 15 streams operating on this list, and there could be another stream operating on this guy. And what does that do? That counts the amount of streams that are currently in here. All right? So thread.active count is getting the amount of streams that are in operation during this guy. Okay? This one here is getting the amount of streams that are in operation, or the amount of threads in operation during this guy. This is going to be the amount of threads that are in operation in the middle of this guy. All right? So we all have a basic understanding of what parallel streams are. Okay? They offer huge performance increases. And that's what threads are all about. Offering performance increases. You don't have to use them. All right? However, they are going to significantly increase the efficiency of your code. All right? It can be the difference of someone waiting 2 minutes to log in rather than 5 seconds to log in. That's the sort of things we're talking about. All right? It's all about performance. It's all about making the user experience of your application better. Okay? So you don't absolutely positively have to use them, but they are going to increase the efficiency of your code. All right? Now, so, and of course, streams didn't exist till Java 8. So none of these guys, parallel streams, existed before. Well, there was something like them, a parallel stream. All right? But threads in Java 7 were a complete and utter nightmare to use. All right? Because you had to manage everything about them. What I mean by that is, if you had a list of something and you had multiple threads accessing the one number in a list, you had to give preference to one thread over the other, and you'd have to tell the other threads that this number is now being acted upon and don't act on it in the future. It was a pain in the arse to use, okay? This is all taken out of your hands now. The thread is dealt with, the executor service thing, or the thread scheduler working background takes care of it all for you. All right? You can still, if you want to micromanage your threads, you still can do that, but life is too short. Okay? Now, so we're going to do static void ex2. Now, we're going to just do a couple of sorted streams, okay? So I am going to create a list of integers, and I'm going to call it list, and I'm just going, it's going to be stream.generate int math.random multiplied by 100 plus 1. I'm going to limit it to, okay, what have I done wrong there? Let me just see. Take this guy. So dot limit, I'm going to limit to 12. I'm going to go dot collectors list. All right, so that's going to create a list of random numbers between 1 and 100, and it's going to be 12, okay? Now, if I want to sort them, okay, we can go list dot sorted, sorry, list dot stream dot sorted dot for each, and I am going to go system dot out println. Okay, so that's going to print off our list in sorted format. Okay, so what does that look like? Let's put in here our list sorted. And we want to make that print, we want them all in the same line. Now, what will that print out if I do that, by the way? What will that print? How will it? There'll be no spaces on our numbers, it'll be like this. Okay, so I don't want that, so I'm going to change this slightly. So I'm going to, so it takes a consumer object, so it takes in a string, and it's going to, or sorry, it takes in an int, and it's going to print off. It's print. It's not going to be a Boolean. We're going to put in a comma between each one of them. Okay, I'll print that out. Oops, sorry. And I need to put in S. Okay. So 3, 4, 9, 23, 35, 53, 69, 76, 78, 79, 88, 89. Okay, so there is our 12 numbers sorted. Just go for a slightly higher number. We'll have 15 numbers instead. Okay, so there's our 15 numbers sorted. Now, of course, if I want to sort a parallel stream, okay, so if I go list dot parallel stream dot sorted dot for each, let's see if this is right. Okay, and if I put in the same in here, okay, so this is our parallel stream. Sorted. Now this should be on the next line. Now, you can't sort a parallel stream, okay? Because its very nature is totally chaotic. Okay, so can you sort? This is an example of certain stream operations, or yeah, operations not working in the same way as with certain stream not working in this, so the certain stream operations not working in certain stream operations when used with parallel streams not working same as with ordinary streams, ordinary single threaded streams. Okay, now it can sort them. Simple as that. Okay? It can't sort them. So what you can try to do is this. So you can go list dot. So again, I'm going to put in another line. So I go list dot parallel stream. So if you want to change something to parallel stream, use the word parallel stream. And again, we go sort it. And then we go for each ordered. Okay. Now, I haven't tried this out yet. That should sort them out. Problem with that is that they're no longer parallel stream. They're now a single threaded stream. All right. So any performance now, up to this point, it's still going to be multi-threaded, but from this point onwards, it's going to be single threaded. All right. So there will be some performance gains, but from this point onwards, it's going to be single threaded. So you're going to lose a lot of the performance. Now, it doesn't make a difference with only 15 numbers. It's when you come to billions of operations, or if you're coming to complex and processor heavy calculations. Okay, doing anything with graphics. Anything with graphics, you nearly always use threads. Anything with video, you nearly always use threads. Anything with sound, you use threads. Games are threads all over the shop. Okay, so anything that's processor heavy, you need threads. So you have graphics, you have video, you have sound, you have any application that takes a lot of processing or threads. The games industry. Okay, any sort of game anyone is familiar with, they're going to be using threads. Now the simpler games, something like Tetris, probably, well, it depends. Okay, so anything that's processor heavy is going to be using multi-threaded. Now here, so list.parallel.sorted for each ordered. Now this should order them in the correct order. I'm going to put it in here. Let's see, does this work? Now it may not work. Yep, it does. Okay. So 17, 27, 35, 41. Okay. Now remember, for each ordered is a terminal operation. Remember that? So that means that none of these guys, parallel stream or sorted, will not run until there's a terminal operation. Okay. So this guy here tells it, oh, this is going to be single threaded. This guy here is telling it, oh, this is going to be multi-threaded because it's a parallel stream.
Everything up to that point is multi-threaded.
Yeah, actually, I think I'd need to check that, Jason. Now that I think of it, I think that causes the whole lot of it to be single-threaded, which would make sense, wouldn't it? I think I'd have to check that. Now, I assume that everything up to that point would be multi-threaded, but now that I think of it, it probably wouldn't be. Because for each order, there's a terminal operation. None of these guys can run until it hits a terminal operation. So that tells it this is going to be single thread. So I am guessing here to say that this is probably single threaded. I'd say. Now I'll have to check that out. Now, it's not just an academic exercise. If the whole lot of it is single threaded, that means it cuts down your processing by a factor of 16. That means that that is going to be 16 times slower than that, I think. So I'll have to check that out. I'll have to do a little bit of Googling. But I think, for the fact that's a terminal operation, none of the intermediate operations will run until the terminal operation happens. So that means that oh yeah, this is going to force it to be a single threaded application. So I'm guessing that this is probably single threaded, but I'll have to find out. Is that okay? So what does this do? Now, this, the for each ordered is a terminal operation that only allows one thread access the stream at a time. So it becomes a single, so it becomes in effect single threaded stream. Okay. So this leads to a loss of any performance you may have gained by using the parallel stream operation. Okay. Now, as I say, I'd have to find out whether you lose all of the gains. My guess is that you lose all of the gains. Now I think of it. All right, because that's a terminal operation. The terminal operation that's telling you only one stream can enter it. So I'm guessing that even though you have a parallel stream, it's still only going to sort it as if it's a single threaded application. Okay, I think. So.
And the one above, it does.
Yeah.
The last operation that's single threaded.
No. For each, that's not thread safe. So that means now, not thread safe is a good thing in this circumstance. Okay, so for each is not thread safe. So that means multiple threads can access the stream at the same time.
Is it possible to call the thread that active count within that stream?
Sorry?
You could call the thread that active count within that stream to check it.
You could.
There's some other way of doing it.
Oh yeah. So you could go sort it. Peak should do it. So peak is a consumer, so it takes a I. Doesn't have to do anything with the I. So we can go system.out. Print, and I could say does that work? I'm going to say thread count is, so it's thread dot what is active count. Now that's going to produce something strange, Jason. Let's see, let me just have a look. I haven't thought this through, so we'll see what happens. So thread count is 16. No, because you see, Jason, you're still at the 16 threads as an operation, but only one of those threads can operate in this stream at a time. Do you get me?
Right, yes.
So there is 16 threads in operation, but only one of them can operate on the thread at a time. That's saying how many threads are available.
Oh, it's not.
Well, no, sorry. It's the 16 threads that are active. Sorry, 16 threads. Yeah. Yeah. But only one of those 16 can access it here. Now,
at that point, for each,
yeah.
Saying before the for each, we're using the 16.
Oh, for the sorted bit. Yeah. I don't know, you see. I don't know, because the for each ordered is a terminal operation. right? Now, it's a terminal operation that only allows one thread access at a time,
Yes.
right? So even though I go parallel stream, that says 16 can use this. The for each ordered only allows one thread access at a time. So I'm thinking that it marks the whole lot of it. So yes, there is, as soon as the parallel stream, it says, right, 16 threads can use it. But I think the for each ordered, it says you can only use one of the 16. As soon as you go parallel stream, it means 16 threads are available to you. If you have stream, that means only one thread is available to you. Now, as I said, I need to check that out. All right. So I need to check that out. Anyway, now we're going to show you the actual performance improvements. So what we're going to do is we're going to do an example of calculating with just 4,000 records of some description. We're going to have a thread.sleep in the middle of it. We're going to see one takes 40 seconds to do. The other one takes 1 second to do. So it's 40 times faster. Okay, so we're just going to get a bit of it set up. So we're going to go static void ex3. So this is going to be the single threaded version. And then we're going to do a multi-threaded version of the same thing. All right, so what we're going to do here, so we are processing 4,000 numbers. Okay, we will do this processing using a single threaded stream, and we will also do the same with a multi-threaded stream, which is parallel stream. Okay, so we're going to see the performances. So all we're doing is we're just taking in 4,000 numbers, nothing more than that. All right. Now, in the middle of doing this operation, we're going to put it to sleep for a couple of seconds. All right. And we're going to show you the performance increase. It's a factor of 40 in this case. Okay. One of them takes 40 seconds. The other one takes 1 second. Now, there's a number being produced in the middle of it. I want to see if you can figure out where the number's coming from, because I don't know where the number's coming from. All right. I should be getting 4,000, but I'm getting 8,000. But that doesn't matter. You're going to see this process takes 40 seconds. Okay. The multi-threaded version of it takes 1 second. We're then going to show you, we're going to be processing 900 million longs. Okay. We have a list of 900 million. I'm going to show you it takes 2 minutes by using a single threaded. By using multi-threaded, I got it down to 0.025 a second. All right, which is what, 80 seconds and 0.25, 800, over 1,000. It's a couple of thousand, right? Anyway, so what we're going to do here is we're going to go, we go understanding performance improvements. Now, so I'll actually change that. We're going to be processing, so put in here, we will process, let's say 500 long numbers, okay, in both a single threaded stream and in a multi-threaded stream, which is a parallel stream. Now, I'll run it in my machine. I don't know what I'll run it in your machine. The reason is it could take too long. Is that okay? So you can run it yourself sometime, but it might take a couple of minutes to run it in those machines. All right? So I am going to create a list of longs. And I could go call it list is equal to stream dot generate. Okay, now what I'm going to generate is I'm going to generate a couple of random numbers. So now they're going to be longs. Now the reason I picked longs is because longs is the largest numeric data type. All right, so it's a heavy load on the machine. You can actually see how long it takes to do something. If there were integers, even dealing with millions of integers, it still does it fairly quick. All right. If you're dealing with millions of longs, you are going to see a difference. Okay. So it's going to be long. We're going to go math.random multiply by 100 plus 1 dot. How's that? Dot limit. Now, the number I'm going to pick is, I do 600 million. 600. Now I do underscores because you can't do commas. Because what do commas mean in Java? What do commas mean in Java? It means some sort of list, some sort of collection. All right, so you can't, if I did 600, comma 000, comma 000, that'd be 3 numbers. Okay, so this is 600 million. So change this to 600 million. Now I'm going to try this. Now, as far as I know, I haven't tried this so far. By doing this, by going dot parallel, as far as I know, that means it's now a parallel stream. I think. I'm not 100% sure of that. Okay, so stream dot generate dot parallel. So it's at that point, it's going to be a parallel stream. What am I going to do? Hiya, Melanie.
Hi, Mel, how are you doing?
Not too bad now at all.
She's in for an information session. I thought I'd swing by.
Grand, Melanie.
Oh, you were in Dublin on Friday?
Yes, got
How'd
on
you
with.
get on?
It was long. It was, some of it was good.
Yeah.
Some of it was very, very long.
Was it?
Yeah, yeah. But
Was it a whole day? Was it?
it was, yeah. So it's
Were you?
yeah. It's. I tell you what, it was an eye opener for the costs involved. Phenomenal.
To hold it?
No, no. If you let's say if you're going to set up a full software company using Azure, I mean, he gave an example of a single machine. It costs 80,000 a month to run,
Lord.
and it wasn't that hard to get that either.
Mm.
So yeah, but it was yeah.
You learned something anyway.
Yeah, yeah, and we all got the vouchers at the end of the development, so it was, yeah, it was definitely eye-opening.
Eye-opening. You said that's a tune earlier, so I don't know what you said to them.
No,
I don't know what you're doing.
So what's today's date?
Today is the 3rd, isn't it?
Yeah. And Roland, do you have your expenses for Friday? Yes, send them on to me, okay?
Just,
And I've collated
you
them.
scan them all. You know,
I put them in a Word document mainly because it's the easiest thing, do you know?
Lovely. And how's everything running here in Amazon?
We'll probably have to get the installs for the Azure, isn't that right, Jason?
Yeah.
Because I can install stuff fine at home, but I'd have to get the installs out. Your man, you're supposed to give us just in the last course, and you've given them to us. So.
We
Okay.
need to turn on remote access.
Yeah, well, if we got the install privileges, we should be okay though. So I'll try and sort it myself, Minnie.
Yeah,
That's okay. If it's not sorted, I'll let you know.
please do.
Okay? 'Cause you know yourself.
Dan is just great crack.
Huh?
It's organized.
Yeah, and well, I made a contact with someone in Microsoft about liaison with here,
Okay,
and they're very interested, to say the least.
in terms of workplace,
Work placement or future courses.
lovely.
And I, well, the idea was whatever course we'd run, it would be Microsoft. To do, basically. And then they would take people on the graduate program.
Oh, very good.
So we don't be on a pair with, let's say, EY or anything like that.
Would you find out an email to me because we're meeting, we have a strategic meeting next week with
Yeah.
Carmel?
Yeah.
And any other ideas?
Now, I know.
Okay, lads, I'll leave you. Good luck. I'll talk to you soon.
Yeah, hold on a minute. I just.
I had to stop the video. Okay, they heard all, everything we said there, Melanie. So I don't think we're putting that video up if that's okay. All right, so we start it again. Now, so I have changed this guy a bit.
You just
Okay,
defrost.
huh?
Just defrost.
Defrost the screen. Okay, that's a new one. Defrost the screen. Actually, that's right. It is defrosting the screen. You're dead right. Right. Now, so now this takes a long time to run on this. So don't bother running it in your machine.
Record.
I am. Okay. So I am creating a list of 90 million integers. Okay. I'm creating a list of 90 million integers. And I'm going, and now what's taken so long to do here is actually this. All right. That's what's taking the time. All right. Now, I was trying to create this list using a parallel stream, but I was doing something wrong. So that's what I was delaying with there. All right. Now, stream.generate, now that is, so the creation of the actual list is done with a single thread, which is why it takes so long. All right. I was trying to actually create it using a multi-threaded, but I was getting array index out of bounds exception. I don't know why. But anyway. So I run this. Okay. Let's see. Okay, I'm going to change that to longs. Just bear with me a minute. And I'm going to change this to longs. And I'm going to run it. Okay, now it takes a long time for it to run. All right, so, okay, that took no distance at all to run. So I'm going to up this a bit. I'm going to up this to 200 million. All right. Yeah, that's a bit more like it. 200 million. So, right. I'm going to up it to 400 million. Going to run it again. Let it run. There she goes. There she goes. So this is taking a bit longer to do. 400 million. No. I'm going to go up to 600 million. Let's run it again. So, she's going to run. She's going to run. Okay, this is taking a little bit longer to do. This is taking a lot longer to do. All right. Now, I'm going to try and up it to 800 million. Now, what I'm doing down here, right, so I'll explain what I'm doing. All right. So, what's taking a long time to do is the actual, this list is being created. There's 600 million longs in it. Longs is the largest numeric data type, right? So, it's going to take, it's harder for it to manage. Okay. Now, then I go here, list.stream. Now, this is single threaded. Okay. This is single threaded. Now, all that's happening with this list, it's going to increment each number, all 6 billion numbers, it's going to increment by 1. Okay, it's just doing some operation. Doesn't matter what it's doing. And so you have time before it, which it was 1359 and 40 seconds, and 1359 and 41 seconds. Okay, so the more longs it has to deal with, the longer it's going to take to do something in here. Okay, now, so I've got 600 million numbers. 600 million numbers takes approximately a second for it to do. Okay, so I'm going to try it with 800 million numbers. Okay, so we got 800 million random numbers between 1 and 100. And we run it. It takes around 1,002, 1,003, 1,004, 1,005, 1,006, 1,007, 1,008, 1,009, 1,010, 1,011, 1,012, 13, 1,014, 1,015, 1,016, 1,018, 1,019, 1,020, 1,022, 1,023, 1,005, 1,006, 1,007, 1,008, 1,009, Okay, that is, let me just see what's happening here. Okay, my CPU is running at 100%. So there's something funny with my machine, because that should be doing a lot faster than that. Ah, yeah, but no. But you see, I have a different version of Eclipse running here, and it runs fine. Okay, so I have a different version of Eclipse running here, running fine. This one isn't. Okay, so I still don't have it. So I'd kill that process, and I'll bring it down to 700 million or 650 million. Now, I run that. 1,002, 1,003, 1,004, 1,005, 1,006, 1,007, 1,008, 1,009. You know, I'll show you the other screen to hell. All right, so I'll stop this guy. All right, so I'll run this one. Okay. Run this guy. Okay. Bear with me here. Mm. Okay, it's still running here. Just, I don't know. Play cards there while I'm waiting for this to run. The only thing that's delaying it is the actual creation of the list. What's wrong with it? Okay, I need to restart my machine. So something eating up my memory here. It seems to be okay. Okay, let's try this here. Okay, I don't know what's wrong with that example. It's just totally, oh yeah. All right. Okay, so it runs on this one here. So I'll just make this bigger. Bear with me a second. Now, so this is all my other code. All right. Now, if I have a look here. All right, so here we have a list of 600 million. Okay, and it's a list of 600 million longs. Now, 600 million longs, that is the largest number type. Well, okay, there is something called a big int. There's also something called a big long, but they're more kind of classes. They're different sorts of classes. But the biggest numeric wrapper type is a long, okay? It's, I don't know what it's, 16 bits or 24 bits or something like that. I don't know what it's, okay? It's the biggest data type anyway, all right? Now, so what takes the long, that takes a minute or so to create 600 million longs. Grant. Now, so I take the time before this stream, okay? So the time before that is 14:05 and 826, okay? And then, so what does it do inside here is that it's going to add a 1 to each one of these 600 million numbers, all right? So this does an action on 600 million longs, okay? Now, it finishes at, the time is 14,
Sorry,
that's granted. Fuck, you put me off my stride now, where am I? Oh yeah, 14:05. Hold on, I need to change this a bit. So it started off with 14:05 and 35 seconds and 826 nanoseconds. Okay, now it finishes at 14:05 and 37 seconds. So approximately it takes 2 seconds. Okay, so a single threaded stream takes 2 seconds to go through it. All right, now by using a parallel stream, the exact same operation takes 314 from 663. That is 339. Yeah. No. 300 and, yeah. 349. That's 349 nanoseconds. That's 349 billionths of a second, as opposed to 2 seconds. Okay, now that's a factor of hundreds of thousands of times faster. Okay, this guy here takes only 345 nanoseconds. So what is it? That is, so that's going to be a billionth. That's going to be 100 millionth. That's going to be a 10th millionth. Okay, so I work it out.
Most of your, in the parallel stream, you print them out, but you're adding up.
I'm not printing them out. Oh no, Jesus, I'm not going printing out.
In one case, there was parallel stream, just sorry, you just
Add
one to.
That's it, yeah.
And then the other one, it would just.
Add one to it as well.
Oh yeah, both, sorry.
You're both doing the same thing. But this one takes a full 2 seconds. This one here takes 349 nanoseconds, which is 349 billionths of a second, which is, so a nano is going to be 0.0000000. It's going to be a billionth or a millionth, 0.0000000. So it's going to be 0.1, 2, 3, 4, 5, 6, 3, 4, 9 seconds, as opposed to 2 seconds. Okay, so that is going to be, if it was 2 here, that'd be 10, that'd be 100, that'd be 1,000, that'd be 10,000, that's 100,000, that's a million. It's approximately 10 billion times faster. All right. So what I said before, it offers multiples of an increase. That is some fucking increase. Okay. Any questions on that? Okay. So it can offer massive increases. All right. Now, I'm going to show you another example. So now this example you will be able to run on your own machine. So I'll just copy all of this code. Okay. And I'm going to put it into my other one here. Now I'll advise you, it probably won't run on your machine. It might run out of memory. No, I think that's nanos. No, it's nanos. It's not milliseconds. Right. So if I go local term that now. All right. I'm just going to get rid of all of this. Now, as far as I know, local time dot now, what it displays is hours, minutes, seconds, and nano. I don't think it's milli. Now I'm open to correction, or actually, I know I'll find out. So if I go local time is equal to local time dot now. So then if I go this in nanos is time dot get nano. And this in milli is time dot get milli. Get, it doesn't actually say milli. So let me just see. So yeah, it is Iggy. See there? Oh no, it isn't nano. Sorry, I stand corrected. That is milliseconds. Oh, let me see. Yeah, hold on a minute now. So that is, so nano's a billionth. That's a millionth. So that's, yeah, okay. So that is, just see, get seconds. Can I get millis? It's too cold now, Merrick, is it? Fuck's sake. What a pile of bullshit. Okay, so that is, let me just say, what the fuck? Yeah, that is, Iggy, you're right, sorry. Okay, that is 0.79 seconds. Okay, yeah. Okay, so that whole one was ridiculous.
So it's roughly about 7 times.
Yeah, roughly, yeah. Okay, so I have it here. So this one here is, it's 0.3 seconds, and this one is 2 seconds, so approximately 7 times faster. Okay, yeah, that makes sense. Fuck's sake, the other one was way too much. Okay, so I'll put it in my other one. Yeah, Kurt, just a minute, man.
You were saying there it's 7 times faster.
Yeah, fuck you. Sorry, I was not cursing you, I was cursing this. Sorry, go on.
7 times faster, that's what we're saying.
Yeah.
But you had 16, didn't you?
Yeah, but you see, but here's the thing. I have a lot of shit happening on the machine. Right, so exactly. Simple as that. Okay. Now you can do something called a priority thread where it'll hog the resources in the machine. You can do that. All right. But I just it's going to use whatever threads it wants. So it can only use 7 at that particular point in time. Now it could have used 10 another time or something like that. And also 7 times as fast doesn't necessarily translate to 7 threads being used either. That's another thing as well. Okay. So I'll just tab everything here. Tab this guy. Tab him. Tab him. Tab him. Now, so I'll say this guy takes approximately 2 seconds. This stream takes approx 2 seconds. And the other one, what did I say, was 0.3, wasn't it? So this one here, this stream takes approx 0.3 seconds. So it's 7 times faster. Okay, all because this is a parallel stream. Simple as that. Forward. All right, so this is 7 times faster. So this processes 7 times faster. Okay, all because it's a parallel stream and you have multiple threads operating on the stream at the same time. All right, makes sense when you think of it. So now 7 times faster does not necessarily mean that only 7 threads are accessing this stream. There could be more, there could be less. You can, but it'll always come up with the available amount of strings are going to be 16. Okay, I would imagine now. I'll just put it in here. So I will go threads dot active count. I don't want to run it because it takes too friggin' long to run. Okay, I'd imagine it will be 16. I'll run it again tomorrow morning myself. It takes around 2 or 3 minutes to run. It's a pain in the arse. Now, if your own machine is better than those machines there, run that at home. Out of memory, yeah. Okay. A lot of things, see, because I have to load it into the RAM, and unless you have a lot of RAM, you can't do this. Okay. Now, if you were going to do something like this, you would then have to test it on various machines. So remember those virtual machines we were talking about? So here's an example where, now, you wouldn't use a virtual machine because they're too fucking expensive. 60 quid. I know you think it's 60 quid for an old shite of a machine that you could pay 300 or 400 euros blowing curries. No. There is, you know, those containers that one of you were talking about there before. Who was talking? Lisa, were you talking about the containers? That was a Jew, Marek. Yeah. Yeah, you were talking about containers, wasn't it? Can you specify the amount of RAM there is in a container, or the container can use? Yeah,
And you're still pulling it from your machine.
yeah. So you'd use container for testing machines with only one core. Now, how would you get it to operate in this? You can use, right, this isn't on the exam. There is something called an unordered list. Okay, and an unordered list is used for parallel processing of large lists. Okay, and it will usually allow machines with only single cores to process large numbers. Okay, and it's also a lot faster than this guy. Now, I was trying to figure it out there, but I was doing something wrong. All right, but anyway, this is an example of, you can see it's 7 times faster, approximately. Okay, now I'm going to show you another example. So,
Up there, no, you had a line 72.
yeah,
Remember before they were doing the parallel, that didn't work, did it?
this here,
Yeah. That was,
it wasn't any faster. It was slower. It should be faster, but it wasn't. It was actually slower.
but does it change from a
Well, basically what you're doing there is, remember that range crack we did with in streams before? Now, in streams are always going to be quicker than a list of integers, because an in stream is just for numbers, okay? And a list is for anything. But an in stream is particularly optimized for numbers. So if you go in streams.range, now when ordered, it means they're going to be all over the place. But it is, so there's no organization going on at all. So it's just spitting out the numbers. All right. So that means it doesn't have to take time to any sort of organization. It's parallel processing, which means it's going to be used, basically going to turn it into a parallel stream. And you do the for each. What I was trying to do in the for each is adding each one of those numbers to the list. But I was getting array index out of bounds exception. And then when I did manage to get it to run, it was fucking shockingly slow. All right, it was taking 5 minutes to do. So now, unordered are not on the exam, but we might come back to them, because when you're using large numbers, they are a lot quicker, apparently. I haven't got it to work at them yet. So I'll just leave it there, even though we're not using it. So what is this guy here? This is a single thread stream. This is a multi-threaded scheme. Okay. Single threaded stream, only one thread at a time. So multiple threads will be used to process the numbers in the stream. So you could have 16 threads operating on the stream at any point in time. Now, each thread is going to be operating on a number, okay? Now, if your machine is doing a lot at a particular point in time, you only might have 7 or 8 threads available. You might only have 2 threads available, okay? If you're running this on another machine, it mightn't even work, okay? Because it's too intensive, okay? It's because there isn't enough RAM to accommodate this boy, all right? If there's 24 bits for each numbers, multiply 24 bits by 600 million, you're getting in the gigs there, okay? You're getting well in the gigs. So if there isn't enough RAM to accommodate those numbers, because that's where the numbers are going to be saved, you get, what was the memory, what was the error you were getting, Visa? Out of memory. That means out of RAM. Simple as that. Okay, if you don't have enough RAM, you won't be able to do this. Now, there is various tricks you can use. All right. But now, so this, now you can run this yourselves, but all you have to do is just decrease the number. Okay, if you decrease that number there, it should run for you. But the thing is, you mightn't see much of performance enhancement. All right, you only really see a performance enhancement when you're doing something that's heavy, that takes heavy processing. All right, or it's a large list of some description. All right, now we're going to do another example where you will see where it will run on any machine. So this one, next one is going to be static void ex4. Just open up my other one here. I'll pull this across.
Against contact reception, John. Against contact reception. Thank you.
Now I'll just put in here, if you wish to run this code, decrease the amount of numbers in the limit until it will run on your machine. Okay, so I have 600 million. You could increase it to 60 million. 60 million should run on your machine. Might take a while, but it should run. Okay, now static ex4. Now let me just see. All right, so this is understanding performance improvements too. So this is another example. Now, I am going to create methods down here, and these methods are going to contain stream operations, okay? So I'm going to create methods beneath static void ex4 that are going to be stream operations, okay? And then I'm going to create static void ex5 is going to use parallel stream operations. Is that okay with everyone? And we're going to see the time difference. All right, now, so we have another method here called public void process all data, and it takes in a list integer data. Okay. Now,
Contact reception. Canteen contact reception. Thank you.
so I'm going to have another method here called public int process record int input. Now, so this method here is going to call this method here. So we're going to send an array of 4,000 numbers down to this method here, okay? This method here is going to have a stream that's going to process all of the 4,000 numbers. And what it's going to do for each one of the numbers, it's going to call this method, okay? So I'm going to have a try block inside here. Now, what I want to do is so each time this method is called, all that happens is that it puts the thread to sleep for 5 milliseconds. Okay? So it puts the thread to sleep for 5 milliseconds. So if you have 16 threads operating on a stream, it should be 16 times faster. Okay? Because you've all 16 threads going to sleep at the same time. Get me? So you have one thread going to sleep at a time, so it goes to sleep for 5 milliseconds. then it starts up again and does its bit of processing. Then it goes to sleep for another 15 milliseconds. Whereas with 16 threads, all 16 threads go to sleep at the same time. It does its thing, then it goes on to the next 16 numbers and the next 16 numbers. So you should see approximately, the other version of this should be approximately 16 times faster. Yes? Is everyone okay with that?
That's the system thread.
Yeah. Well, it'll be the system thread, or now I'm going to using this. I'll use this method with the other one as well. Okay, we'll have the 16 threads going to sleep at the same time, but then the 16 threads will wake up and they'll be processing 16 numbers. Now all that's happening with each of the numbers is it just goes to sleep for 5 milliseconds, 5 thousandths of a second. Okay, now that has to be the try catch block. So I'm going to go here, catch, INTERRUPTEDEXPTIONE. Now, I don't care what number I'm returning, I'll just return any shit at all. So return input -1. Now, so what I'm going to do here is, so this process all data is going to call process record. All right. So I am going to go. I want to see how many records have been processed. So I'm going to go data, stream, .map. Now the reason I'm using .map is I am taking in a integer and I'm passing out this integer. Okay, so if I take in the number 4, so this is going to be processing 4,000 numbers. Okay, this is going to be processing 4,000 numbers. So if it takes in the number 4 as one of the numbers, it's going to return the number 3. Okay, doesn't matter what's returning there. All right, so map, and I'm going to say it takes in a number, and each time it's going to call process record A, and I'm going to go dot process record dot count. Okay, so what's going on here? So we will send our list to this method, which contains our numbers. For each number, a thread that is dealing with the number will sleep for 5 milliseconds. Okay, as this is a single threaded stream, only single threaded stream, a stream will sleep, then perform an operation. And we'll do this 4,000 times, as we have 4,000 numbers. Okay, so it does it sequentially, one after another, and that takes a set amount of time. All right, now what are we going to do? So we're up here. Yeah. Yeah. A map is usually used for conversion from one type to another. Okay, in this case, it's not doing a conversion at all, but it is. Okay, it's taking in. So let's say you've got. Now you're going to have 4,000 numbers. Let's say if the number is 5 and the number 6 and the number 7 and the number 12. Okay. Now, so it takes in the 5. It's going to send the 5 to process record. What's the first thing that happens? It goes to sleep for 5 milliseconds. Okay. Then it returns 5 minus 1, which is 4. We don't care what the number is. It could return anything. All right. Now, if you want to do something with the number or do something with the value inside the stream, you use map. Okay, because map doesn't change the original number. It produces a new number. Do you understand that? So map doesn't change the original numbers inside here in data. Map produces a new number. Okay. Now, that's very important when we come to, what are they called in it? I need to get the name of them. Stateful lambda expressions. Okay, so we'll be using map an awful lot more when we come to something called stateful lambda expressions. What a stateful lambda expression is that the stream shouldn't change the original source data. Map does not change that guy. Okay. Well, no, because map, right? Map takes a function. What does it take again? Yeah, it takes a function. Okay. So what it does, it takes in the number and it produces, in this case, a new number. But it's not assigned to the list. It's not assigned to data. Do you know what I'm saying? Whereas if you used a for each can change the data inside this. All right. This is not changing it. This is producing a new number. Do you get me?
Yeah, but its function doesn't have a name.
No, it's function. It's a function. A function, you know, a function takes.
Sorry,
yeah.
I keep getting
Yeah.
mixed up, yeah.
Function is it takes in something and returns something. Okay. Now.
And just that's the contents of the contract.
Yeah. Now. The count is producing a funny number here. I don't know where it's getting this number, so maybe you can work it out for me. It's meant to produce 4,000. That's producing 8,000. So maybe you can figure out. Now, I knew when I was doing this before, I knew what it was, but I forgot to put down a comment. And I'm not too sure where it's getting the 8,000 from. All right? But anyway, so I want to get this done first. So to use these methods here, we have to create an examples object. Okay, so I'm going to go examples. ex1 is equal to new examples. And I'm going to create a list integer, and I'm going to give it the same name as this guy here. I'm going to call it data. Now, I'm going to go stream dot iterate. I'm going to start off at 0, and it's going to add 1 to each number. It's going to limit it to 4,000 numbers. And we're going to go collectors. That should work. Let's just have a look at it. Now, just to make sure it's of the right size. Should read 4,000. Oh, 4,000 should be, sorry, change that to 4,000. Now, very simple list. It just starts off at, what does it start off at actually? Let me just say. It's data, all right. Starts off at 0 and it should finish at 3,999. Okay, so it goes from 0 to 3,999. Okay, so don't need that there anymore. Right, now, I've done a different way here for getting the time. Apparently this is more accurate, but we'll have a look anyway. So, use this, long start is equal to system dot current time millis. Now, what is that? That is the amount of milliseconds since the first of the first 1970. Okay, that's the amount of milliseconds since the first of the first 1970. Now, current time millis. Yeah. Okay. So that is the amount of time since the first millisecond on the first of the first 1970. Okay. Now that's computer time. Computer time is it's not done from the year 0. It's done from the year the first 1970. So when you're doing current time millis, that's the amount of the milliseconds since the first second millisecond, the first 1970. All right. So that's going to be our start time. All right. That's going to be our start time. Now we are going to go ex ex1 dot process all data. Okay. Now, so it's going to send our array of 4,000 numbers down to this guy. The first thing that's going to happen is that it's going to put the thread to sleep. Now, there's only one thread dealing with all 4,000 records. So it's going to check it, go to sleep for 5 milliseconds. It's going to return, so the number's 0. It's going to send 0. So that's our list. Contains the numbers 0 to 399. So it's going to send all the numbers here. Then it's going to send each one of the numbers. It sends 0. It goes to sleep for 5 milliseconds. Then it returns -1. It sends the next number, which is going to be 1. Then it puts itself to sleep for 5 seconds, 5 milliseconds. Then it's going to return 0. Then it sends the number 1, number 2. It goes to sleep for 5 milliseconds. Then it returns 1, and so on and so forth. It does for all 4,000 numbers, but it does them one at a time, as opposed to if it was multi-threaded, you could have 16 numbers being accessed and 16 numbers being changed at the same time. Okay, so ex process 1 data. Now, so we know what time it starts. So if we want to get the amount of time it finishes, so we go, now for some reason or other this returns a double, I don't know why. So I go double finish is equal to system dot current time millis minus start. Now, let me just see what a long go there. I don't know why I put a double in there, but I'll leave it there for now. Now, so if I go here, so that's the time it started. Okay. Then it does its thing. Takes a couple. So let's say that this is 11011. Okay, milliseconds. And when it finishes, it's going to be 100200. All right. That means 100 milliseconds has passed. All right. So then I just go the start, which is that guy. So it's going to be the current time minus start, which is going to be 100100, and that gives us 100 milliseconds. So we know how many milliseconds it took. All right. So
That's including the thread speeds as well.
but you see, there's only one thread here. Oh yeah, yeah, it is include the thread sleeps. Yeah. But what it doing, as there's only one thread in it, it does its thing, it goes to sleep. It does its thing, it goes to sleep. It does its thing, it goes to sleep. As opposed to 16 threads, you have 16 numbers being accessed at the same time. All of those 16 are going to go to sleep at the same time. And they're all going to wake up at the same time. So it's going to be 16 times faster. Okay? Think of 16 people doing their work instead of one person doing their work. The 5 people are going to be 5 times faster than one person. Makes sense. Okay? So I want to see how many milliseconds. So this has taken milliseconds. Now, if I want to this is the right one. And I want to see how many threads are in operation at this point in time. So I'm going to say I want to see how many threads are in operation, amount of threads in operation. It's going to be plus thread.activeCount. Now, this takes around, I think this takes around 20 seconds to do. Okay, so I'll run it first and then you can try it, see how long it takes. So yeah, so it should take around 20 seconds to run. So here we go. Okay, so let's see. Now it's, if I didn't have the sleeps in it, you see, it would just race through it. All right, when you put the sleeps in it, it forces it to go to sleep for 5 milliseconds. All right, so you should see the difference when we're using a multi-threaded application. Now, 20 seconds is what it was taking. It might take more. Okay, so that is 22,986 milliseconds. Now, if you want to convert that into seconds, what do you need to do? How do you convert that into seconds?
That's 30 seconds, isn't it?
Milliseconds, thousandth of a second.
You have to turn it into what?
Seconds.
5 by 1,000.
Divide by 1,000. Okay, so now, and see here, one thread. All right, so I'm going to run it again. So that took 22 seconds, well, 23. So it's So it gets the 4,000 numbers very quickly. Okay. And if I didn't put in the sleep, as I said already, it would just fly through it and you wouldn't see any appreciable difference between single threaded and multi-threaded. If you put in a sleep, then you can see the appreciable difference. All right. So last time it was 23 seconds approximately. So it's around 23 seconds again as well. Okay. So that's not milliseconds. That is seconds. So is everyone with me so far? Yes? Right. Now, we are going to do exactly the same thing. Okay. Now, so that is EX4. The next one is going to be EX5. Now, I am going to do the exact same in EX5. Now, the only difference that's going to be is the process record thing, okay, or this guy. So we're going to have another one. So it's going to look the same. Now, this is going to process all data 2. All right. Now, the only difference is going to be is that this is going to be P-A-R-A-L-L-E-L, capital S. All right. Now, so process all data 2. Okay. Now, the only difference with this one is that this is a parallel stream. It's still using process records. All right. It's still using processed record, which is fine. Okay. But this is called process all data. I'll actually call it PAR because it's parallel. It's a better name. PAR. Okay. Now I'm going to run this one. All right. So this is EX5. Now this one took 23 seconds. First one. Okay. There we are. 1.448 seconds. And the other one was taking 23 seconds, was it? It's around, still around 7, 8, 2, 10. How many times faster is it? 15 times? 15 times faster? It's actually not far off 16 times faster. I'll run the two of them side by side. All right. So I'm running the first one. So this is around 23 seconds, I think. Whenever it decides to come up. Right. Okay, so the first one took 23 seconds. Amount of threads in operation, 1. The second one took 1.447 seconds. That's approximately 16 times. So guess what? It looks like all of our threads are being used for the second one. Approximately. Okay, so this one takes 23 seconds. This one takes 1.447 seconds. Approximately 16 times. Yeah. Sorry?
Minus 5 seconds with the 4 threads.
Minus 4 seconds?
Mine is 5 seconds.
Oh, yeah, yeah. Oh, yeah. Okay. So you've 8 threads, isn't it? 4 threads? 4. So it'll probably be 4 times slower. 4, what is it, 5?
I'm at 5.4.
5 ones. It's not far off 4 times. And the difference. Okay. So you can see the different amount of threads results in. So I'm going to put in the comment here. The only difference with this is that this method uses a parallel stream. And this is done on, so the time and the time taking to do this work is approx 1.5 seconds, we'll say. Seconds, which in my case is approx 16 times faster than in EX4. Okay, now you need to substitute in whatever you got there yourself. Okay, and you need to substitute in whatever you got there yourself. So if yours is 4 processors, you put in 4. Okay, now as we have 16 threads in operation, it seems that all the threads are being used by parallel stream. Okay, that takes 1.5 seconds. This one for me, this takes approximately 23 seconds. Okay, so, and dependent on how powerful their system is, that's how long it's going to take. So you could ask the question, how long will this application take to install on a particular machine? It depends on how many threads have access to. How long is it going to take a result to come back to the user? It depends on how much threads your system can handle. All right. So you could imagine a situation where if it's got a powerful machine, if there's a lot of threads in operation, if it's an octa-core system, what Joanne was talking about in Microsoft, didn't she mention something about 124 cores at one stage? Didn't she? So 124 is multiply that by 4. It's a fucking lot. 4 ones is 4. 496. You'd have 496 threads in it. Now, obviously, that's an insane sort of a machine, but you can get them. Wasn't that the one where your man was talking was 80,000, wasn't it? Okay. So, you can see here how much faster. It's approximately 16 times faster. All right. This one here is approximately 23 seconds. This one here is 1.4, 1.5. It's varying between 15 and 16 times faster. Is everyone okay with that? Yeah. So parallel streams can offer large performance increases. Now, it depends what you're designing for. All right. If you're designing simple software for simple devices that's going to have limited power, limited RAM, only one CPU, then threads really aren't much use to you. All right. Threads only come into their own when you have multiple cores that can be used. So if you're putting any software on a server, now server, if you're putting them on a Microsoft server, you can be sure they have got cores coming out their wazoo, okay? So if you're putting software on a server and it's a Microsoft server or Amazon server or Google server, you'd be made not to use threads. You will see huge increases in how fast your application runs. All right? Because they're going to be professionally run servers that are going to have God knows how many cores, God knows how many threads can be run. So your application could go like that. It could be literally lightningly fast. All right? So do we understand what parallel streams are? Yes? Do you understand the performance increases you can get from them? All right. Now,
And just know the count there is just what counting up that you reached.
Yeah,
4,000.
yeah, that's it. That's exactly it, Kieran. Okay. I had a previous example here and I was getting 8,000. I don't know why, but I'm not getting 8,000 here, which is good.
And count is the terminator.
Yeah, terminal operation. Okay. The reason I put that in there because it's a terminal operation, Kieran. That's the only reason.
Okay, yeah.
Because I didn't want to print off all the numbers. All right. And you can see the 16 threads here. And this one here, there's only one thread in operation. Okay. Now, so the reason I have the sleep in here is because each thread will sleep for 5 milliseconds. So if single threaded, it goes sleep, process number, sleep, all one after another. However, if it's multi-threaded, you have 16 threads. So 16 threads go to sleep at the same time, wake up at the same time, and process 16 numbers at the same time. Then goes on to next 16 numbers. So in the time it takes one thread to process one number, a multi-threaded application could have 16 numbers processed. Now I only put the thread in there, thread.sleep, to simulate it doing something. So it's connecting to a database, it's waiting for connection, whatever. Okay, 5 milliseconds seems fine. You can put in a larger amount to see a larger gap. Okay, if you put in 10 seconds, you should be seeing approximately 40 seconds of a difference. Actually, I'll put in 10 seconds to see what happens. So at 10 milliseconds, that's 0.01 of a second. So we should be getting around 40 seconds and we should be getting 2 point something. So I'll let it run. It should be around 40 seconds should take to do, and then the other one should take around 2 seconds, 2.5 seconds. So it's going to go to Come on, come on. Should come off fairly soon now. Should be, yeah, okay. Right. Yeah, so 42 seconds. Right. And then we have the other one took 2.7 seconds. So yeah, that's pretty close to 16 times. Approximately 16 times. Right. So now maybe on your own machine, you want to decrease that to 1 second, whatever. All right. But I'm going to leave it at 5 seconds. So you can see there the difference multi-threaded can make. So there's roughly a 16%, there's a 16 times, there's a 16 times increase in performance. Okay. Now, so I put in a comment here about it. So I will put in here for parallel streams. Okay, so this is a general comment for parallel streams. Okay, so the more CPUs you have, the better the performance. So scaling is the property as we add more resources, the results gradually improve. Okay, so if you get new hardware, if you get new machines, if you put all RAM in your machine, if you buy those hideously expensive virtual machines in Microsoft, okay, and rather than just have a CPU that's running at 2.4 gigahertz, let's say it's running at 10 gigahertz, right, which is going to, and it's a octo core. I don't know what you call for a 16 core. Hexacore, maybe, would it be? I don't know. Whatever you call a 16 core machine, okay? And your man the other day was talking about a 128 core machine, or was it 456? Something ridiculous, anyway. All right, so scaling is the property to add more resources. We add more resources. The property as we add more resources and the results gradually improve. Now, what I mean by that is, before we would create all the way up here a list of 600 million, we wouldn't do that. We'd have to make sure that that can work on every type of machine. Now, it doesn't work on your machines there. So what would we need to do? We'd need to split up that list into 2 lists of 300 million each. Okay, and what you could do is you could test the machine to see how many cores are on the machine. So if threads.active amount is greater than 4, use that. Else, split it up into 2. All right, so you can check the amount of available cores at any particular point in time, and you can call a single threaded or a multi-threaded version. Okay, so where are we? This guy. Scaling the property as we add more, the results will gradually improve. Okay, so improvements in performance using parallel streams are often only noticeable when using streams with large amounts of elements or when processing complex tasks. complex tasks. Okay, so I'll just say here, games, video, all use parallel streams. You could say or all use threads. Most of them wouldn't use parallel streams yet, but games would use threads. Video would use threads because you want to squeeze all the maximum amount of power out of your machines. For instance, in games, there's something called overclocking. Okay, now what overclocking is, you have a specific graphics card for games. All right, you have a different graphics card. You have a separate graphic card that handles the graphics. Overclocking, so it allows your CPU to run faster than it should. Now you need to be, so that would mean that you can squeeze more threads out of it as well. Overclocking is all about squeezing more threads out of the CPU. Now, do that wrong, you can set your machine on fire. Literally. You can cause it to, your CPU heats up too much. Can't handle it, so it goes on fire. All right, but that's all about getting more threads. So games, video, use threads. EA, one of the biggest games company in the world, they're up there beside Boston Scientific. Okay, you wouldn't think it. They're fairly low key. There's a couple of hundred people working for them. All right, they all use threads. With large amounts of elements or when processing complex time, games, video all use threads. Okay, for small, yeah.
Sorry, can you squeeze more threads out? We got 4 CD and gaming, yes, whatever.
I don't know how it works, Kieran.
Oh yeah, that's right.
To be honest now,
That's
yeah, it's through the virtual cores, I think they're called. But you can't. That's what overclocking is all about. It's for getting more threads. The more threads you have, the more processes that can run. That's all it is. So for small streams, the improvements are often limited, as there are some overhead costs. Allocating and setting up parallel processing. Like, it's not cost free. Okay. Right, that's not bad. Right, so now, so processing threads. Now, when you're using parallel streams, what is important is you need to consider each one of the objects in the stream should be independent of one another. All right, what do I mean by that? If we have a stream, all right, and the stream is just a series of random numbers, 4, 56, 98, 100, 250, right? They're just a series of random numbers. So they are perfect for using with parallel stream, right? Because there's no order to them. And also that 4, so we have 56, that's totally independent of any other number. In other words, I don't have to do something to 4 to arrive at 56. I don't have to do something to the 56 to arrive at 98. I don't have to do something to the 98 to arrive at the 100. I don't have to do something at the 100 to arrive at the 2. I don't have to do something to the 2 to arrive at the 50. Do you understand that? So independent data in a parallel stream should be independent. There shouldn't be any dependency between the first number and the second number. There shouldn't be a dependency between the first number and the last number. So random numbers, there is no dependency amongst them. If there was, you should not use no parallel streams. If you do, oh sweet Jesus, I'll show you what can happen.
You mean like if they're ordered?
Well, so let's say we're starting off with a random number between 1 and 100. And let's say that it,
Well, you were saying random numbers, you could get the same number. couldn't you?
you can. Well, you are. When you're doing a list, you can. A set, no.
Yeah, we're doing this. Like,
Yeah. I want, so when I did the, see here, limit 4,000. Now I did stream.iterate. That's going to start at 0 and it's going to go to 3999. Okay. Now, if I did a generate there, and you know, I did int math.random multiplied by 100. All right. If I did that, that's going to produce only numbers and plus ones. Only numbers between 1 and 100. Okay. Now, if I produce 4,000 of those numbers, you are going to have repetition. You have to. Okay. If I produce 900 million of those, you're going to have millions of numbers repeating. Yeah? Right. How was the question?
I was about being independent. If you get the same number repeating.
Right. So, no, here's what I mean by independent. Okay. Let's say we're going to start off with a number. Now, the number that's generated can be totally independent. The number that's generated can be totally random. So let's say the number produced is 365. Now, we want to produce a list from that number. And all it is we're going to add 2 onto that number and every other subsequent number. So then it goes 365, 367, 369, 371, etc. Right? Yeah?
Yeah.
Right. Now, so that means, now these are, we could say they're live numbers. This number is dependent on this number. This number is dependent on this number, which is dependent on this number. This number is dependent on this number, which is dependent on this number, which is dependent on this number.
But once it's created, it's only independent. How is it dependent?
Well, no, what I mean is, right, so you want to keep those rules.
Right.
Do you get me? If you want to keep those rules, you can't use parallel streams on it. Because as soon as you use a parallel stream, what does it do? Parallel stream comes in like a wrecking ball and just, it doesn't give a shit what 16 numbers it takes. It's just going to take those 16 numbers. Okay? So it's not so much that you can't do it. If you want to keep the rules, you can keep the rules. That's what I mean, Jason. Is that okay?
Yeah.
All right. So,
You know, if you did, remember, if you did generators, so you get duplicates, right? In the
yeah,
list.
yeah.
And then if you do something with that list,
Mhm.
would that be a problem then? Because you might be trying to put the same number, 2 different parallel streams from the same number in or out. Right?
No, no, no. The I'll say it just. The stream scheduler knows what numbers it's used already. So you're saying
Instead of 299.
yeah, so you've 99 and you've 99 and you've 99 and you've 98. Okay. Now, if it's a list, it'll put in all those numbers. So what you're asking is, how does it know it's already put in that number into the list? Is that what you're saying?
Yeah.
It's the thread scheduler knows what's gone in. Okay. And anyway, hold on, because it's just spitting out numbers. There's no, all it's doing is stream.iterate or stream.generate. It's just creating numbers. And as the numbers are being created, that could be added to a list. It's just spitting out numbers. It doesn't need to keep track of them. Because there's no, I haven't put any limits on them. Because if I use stream.generate, right? So that's producing random numbers. And it can produce 99, 99, 98, 98, 100, and 2. They're all just going to be added to the list. So generates 99, adds it to the list. Generates 99, adds it to the list. Generates 98, adds it to the list. Generates 100, adds it to the list. Now, if it's a parallel stream, oh, yeah. Here's the thing, right? Parallel stream and generating don't really work that well. Okay? Parallel streams are usually used in conjunction with an existing list, set, or some collection object. Usually. All right? Now, as far as I know, I don't think there is a generate with, let me just see, data dot.
Generate is
Yeah, P-A-R-A-L-L. No, it's not. Yeah, L-E-L-S-T-R-E-A-M dot. No. So stream dot. No. I'm nearly certain you can't go parallel stream dot generate. Let me just see. So it'd be P-A-R-A-L-L-E-L-S-T-R-E-A-M dot. Bollocks. No, I don't think you can. Let me just see. Give me a second. Oh, time is up. Fuck it. Just as well. Saved by the bell. Okay. So I'm going to stop the video.